So what I'd like to do is, and I'm using a slide deck, as you can see, from February that I gave at Tel Aviv University. But I'll share more details about the general problem we're looking at, and this is like deep down underneath our version of ZKPs lies. I mean, the whole process that we follow is one of arithmetization, as I discussed last time, of taking like a general computational problem and converting it to some other mathematical algebraic. Sorry, my daughter just left for school. Into some algebraic problem. And this algebraic problem, now you sort of completely forget about computation, and it is only a question of proximity to low-degree polynomials. And I want to tell you about a few efficient algorithms for this. So, and then this talk will be very different from last week's. It will be very math-oriented. And please, I'll pause from time to time to ask if there are questions, but also don't hesitate to stop me. So the Reed-Solomon code is a linear code. So it's convenient to call it V. Just one second. Nitzan, sorry. So the Reed-Solomon code is a linear code over a finite field F. And in a more general form, you also have an evaluation domain D. D is a subset of F. And then you have a degree parameter, which is little d. And the members of this linear space, this linear code, are all evaluations of degree little d polynomials, where the evaluation is over the domain capital D. So often, I mean, in many cases, one takes capital D to be all of the field, or maybe everything but zero, but it's important for us to also allow the more general setting. Okay, so this linear space is a very well-studied and elegant space that has a lot of nice properties. The rate of this error correcting code is denoted by rho. It is the ratio between the degree plus 1. Notice that in our case, we're looking at all polynomials of degree strictly less than little d. So you have d plus 1 you have d coefficients representing, or d degrees of freedom, because you have coefficients from a0 up to a d minus 1. So your rate is defined to be capital D over the size of large D. I now realize that, at least for Zoom purposes, using capital D and small d is very problematic. I hope will be understood. Now, the general question that is studied in a lot of the papers, including the one that I sent to Veronica yesterday, is the following. It's a question about average case to worst case, or worst case to average case reductions. And the question is phrased as follows. Suppose the G is a function that is delta star far from the vector space. Now, in all of this talk, distance will be measured by the relative Hamming distance. So the distance is the fraction. So when we say that G is delta star far from V, what we mean mathematically is that delta star is the minimal fraction of the entries of G, thinking of it as array or a table. It's the minimal fraction of entries you need to change in order to convert G into something that belongs to V. So it's called the relative Hamming distance. Relative means it's normalized, or the normalized Hamming distance. It's normalized by the block length, by the size of capital D. So it's always between 0 and 1. 0 is when G belongs to V, and 1 would ideally be when you need to change all entries of G in order to make it in V. Okay, so the question we study over a number of different papers is, assuming G is some maliciously picked function that is delta star far from V. And assuming also that H is an arbitrary function, also picked by a malicious adversary. We would like to say that typically the distance of something along this affine line, so having G as its origin and going in, with slope alpha, we would like to say that a random point on this line, which is it's a vector of dimension capital D, we would like to say that it is also typically far from V. So that's the question. Okay. And all the results that we have sort of deal with this particular question. We want to prove lower bounds on delta average, on the average case distance on this line, and we generalize it to spaces and curves and other objects generated by G and H, or maybe by G and a bunch of H's. We would like to say that as long as G is very far, maximally far, something very far from V, then no matter how you try to mask it with this H, the sort of affine space generated by G and H, a typical element there will be far. So that's the question we studied. Any questions about just this? I'll pause here and ask, are there any questions about this particular question and the setting?
So here the alpha is uniformly random in the field.
Yes, alpha is sampled from the field. You can generalize it to some, an extension field or a subfield or some specific set, and all the results that we have generalized very nicely to these settings. But yeah, alpha is, you're right, alpha is in the field.
Okay, thanks.
Was there another question?
Yeah, maybe just very general question. Why are you using Reed-Solomon codes in this deep FRI code?
Okay, so
the other code, why codes?
Yeah, so generally speaking, I'm not sure if we covered this particular thing last week, but maybe okay. Let me say it, and I can refer you to material or webinars on this aspect. Arithmetization takes as its starting point a computational problem and ends in questions that are similar to this one, but they sometimes can also be phrased over multivariate polynomials. Now, why do they use polynomials as their end state? I confess that it's somewhat mysterious even to me. I can mention the kind of properties that polynomials have that make them really good for being the end point of reduction. First of all, they form a very good error correcting code. In the case of Reed-Solomon, it is an MDS code. So the sum of the rate and the distance of the code is 1. And that's the best you can hope for. So they're very good codes in their error correcting properties. Another property that is very important in arithmetization is that polynomials have what is known as the multiplication property, which means that if you take the pointwise product, so if you have G and H, and suppose G and H in this case belong to your code, and now you take the pointwise product of entries, right? So it's some weird operation from an algebraic point of view. So what you get, if you started with Reed-Solomon codes, what you get of degree D, what you get at the end is some member of the Reed-Solomon code of degree 2D, which means that the span of all such objects is still a pretty good error correcting code. It has distance, 1 minus 2 rho. So, and often this is good. So that's the second property. One is they're very good error correcting codes. The second one is that they have this multiplication property. And a third one, I mean, there are two more. An additional one is that they have a very rich automorphism group, which means, so as an error correcting code, it means that, if f is a polynomial if f of x is a polynomial, then f of ax plus b is also a polynomial of the same degree. And this is very important in wiring and so like the error correcting code is used for soundness, and the soundness of the systems usually relates to the distance of the code. The multiplication property is really, really important because Reed-Solomon code, or in general, polynomials are closed under addition. So, thinking as you want to encode computation by some error correcting codes. So addition is given to you for free if it's a linear error correcting code, and multiplication by scalars, same way. What you're missing typically is multiplication. And it turns out that the multiplication property of polynomials is what allows you to encode multiplication gates. And if you have addition gates and multiplication gates, that's enough to encode all computations informally. The third property is important for wiring, for taking a general computation and somehow converting it into something that has nice structure. And for that, you use actually the rich automorphism group of codes, which means that of polynomials, which means that if you apply a linear transformation to the variables, you are still looking at a low degree polynomial. And the reason it's important is if you want to talk about, like, say, some other gate, and this other gate is given by a linear relation, then you can sort of look at f at the point x, and f at some linear transformation to x, and it will give you, some relation between these two wires or two gates. And then there's one additional property, which is that some polynomials are very succinct. For instance, if you have a subgroup of size k, and you want to take the characteristic polynomial for this thing, so the polynomial that splits to all roots that are in this group, then that polynomial is just x to the k minus 1, right? Because all elements in this, all kth roots of unity are roots of the polynomial x to the k minus 1. And this is used for succinct representation and succinct verification. So I mentioned, I went sort of on a detour, and I mentioned 4 properties of polynomials, and this is true for multivariate and univariate polynomials as well. 4 properties of polynomials. They are good error correcting codes. That's used for soundness. Soundness is related to the distance of the code. They have the multiplication property, which is important for encoding arbitrary computation, including multiplication gates or AND gates, same thing. They have they're closed under a rich group of automorphisms, basically the affine group, and that is very important for wiring and sort of talking about different gates and how they relate. And finally, certain subsets of a field have a very succinct representation, and that's important if and only if you care about succinct verification, because that's used in those settings. So now you could use multivariate polynomials, and indeed many of the original constructions, so the famous IP equals P space result of Shamir and MIP equals next result of BFL of Babai, Fortnow, and Lund, and a bunch of other results in the early days of PCPs used only multivariate polynomials. Starting with this work that I did with Madhu Sudan in 2005, roughly, we showed how you can use univariate polynomials, which are Reed-Solomon codes, to get quasi-linear, to get the most efficient PCPs. And that was sort of the starting point for using univariate polynomials, which are much more efficient in terms of the rate to distance ratio. They're MDS codes, and they also have very efficient encoding and decoding algorithms, so bringing them back to the forefront. Sorry, not bringing them back, but bringing them to use in the context of proof systems. So I gave a very, very long answer to this short question, but I can happily refer to. So I don't know if I told. I think Veronica knows that I have this Crowdcast series, and all talks have been recorded. So I have a specific talk on arithmetization, which sort of deals informally with this question of why are polynomials useful. And I can share the link later on, and you can later watch it.
Yeah, I shared it with the group already.
Okay, good. So
may I ask another question? Sorry.
Yeah.
Yeah. So so you are hoping to bound this delta average from below by delta star in terms of delta star, and also maybe D capital, like a small d somehow, or no? What sort of bounds are you?
Yeah, we'll see it in a minute. We'll see that you have some relation on some dependence. According to our current understanding, the lower bounds that we prove also have dependence on rho, or on little d, on the ratio between little d and big D. Yes, but yeah, you would like it to.
Okay. And the next question is about the delta. So delta here is the distance of a polynomial from a space, right?
Yes, which is
the Hamming distance?
Relative Hamming distance. So it's or fractional, right? It's a number between 0 and 1, and you take it to be, so the distance between an element and a set is the minimal distance between an element and some member in the set.
Sure, thank you.
And it's always between 0 and 1. Okay, good. So now I want to explain why or how FRI works. And FRI is the main, so there are, like, briefly, I'd say 3 components in a start. There's arithmetization, which is, if you saw one arithmetization, let's say in the IP equals P space proof, then it will look similar. It's sort of converting in a fairly natural way, at least initially, problems of computation. There's the heavy hammer of soundness, which is the proximity protocol, and FRI is one. And then there's the crypto, which means, we argue everything, and everything I'll say today is in this idealistic, ideal model that is not realistic. It's called the IOP, the Interactive Oracle Proof Model, where we assume this is what is explained in this slide. We assume that we are given Oracle access to the function f, and we would like to design a protocol that distinguishes with minimal complexity between 2 extreme cases. Either f is in the code, in which case the verifier should accept, or that f is delta far, and think of delta as pretty large from the code, in which case we would like to reject with high probability. And all the protocols that we're going to define will have perfect completeness, meaning that if f is in the code, you will accept with probability 1. So your soundness error, the soundness would mean that in the second bullet, in the second case, you would like to reject with as high a probability, and that's the soundness. Or the soundness error is 1 minus the soundness. It is the probability that you are fooled into thinking that f is low degree, whereas actually it is pretty far from being low degree. And we work in this model where you have a prover and a verifier, and the prover is trying to convince V that f is close to the code. And the particular model we have is this unrealistic model, but very convenient from a mathematical point of view. And it's called an IOP of proximity. So, and it's depicted here on this little, diagram. So the prover, we assume, I like to refer to these as USB sticks. So maybe that's a good analogy. So the prover sends a USB stick to V. So a USB stick is something that you can, an ideal USB stick is something, you commit it to, you can't change what's written on it. And then the verifier can actually read, have random access to the contents of this USB, as opposed to a Turing machine where you need to read everything in order to reach some position. And then the verifier responds with randomness. In our particular setting, everything will be just public random points. You could define systems where there's some secret that V has, but all our protocols just ask for public randomness. And then in response, the prover sends the next USB stick. And this goes on for a number of rounds. And at the very end, the verifier will use more randomness and then read a bunch of queries from all of these USB sticks, run some computation, and output a decision that is accepted. So this is the model. And as I said, we have three components. One is the arithmetization, which reduces the problem to proximity questions. The second one is the focus of this talk, and that's where, that's where the heavy hammer and the beautiful math goes. It's solving this problem and understanding and devising protocols for it. And there's a third part to Stark's, which is using crypto, so either collision-resistant hashes or the random oracle model, if you want to make it a non-interactive proof, in order to realize these oracles, right? So instead of an oracle, what really happens is the prover sends a Merkle root to the verifier. And if you want it to be non-interactive, the randomness is even replaced by a PRF applied to that root, and you're using the Fiat-Shamir heuristic. Okay, so, but our focus is the second thing, which is the most beautiful and significant part. It's the low degree testing. So what is FRI? FRI, as its name suggests, and it intentionally refers to the fast Fourier transform, because actually one way of thinking of it, as you'll see, is as a folded FFT. So it is a protocol in the IOP model, and it works when your evaluation domain is FFT friendly, meaning it's a subgroup of order 2 to the k for integer k, which is the same setting that you see the FFT in its first incarnation. So we need the evaluation domain to be that thing. There's some recursion going on, and you want to always be in a sub problem that is of the same structure but half the size. And in this model, the prover time is linear in n, and prover time is the number of arithmetic operations, each multiplications and additions in the field f. So the number is not just O of n, but the constant in front of the O is at most 6. So it's a very small constant. The verifier time is not just logarithmic in n, its constant is at most 21. And the query complexity itself is log n. So there's no, notice there's no O notation so far. The number of rounds is log n, number of rounds of interaction, because I mean, it's going to look like FFT style, where you start with 2 to the k, you go down to a problem size 2 to the k minus 1, 2 to the k minus 2, so on and so forth, till you have a constant size problem. And the rejection probability of words that are delta far will be delta, for sufficiently small delta. And a lot of the work is on proving this, and this is true for all works on IP and PCP and MIP, and soundness is the toughest part, always. In all works I know about PCPs, it's the soundness that is the most difficult part, proving that the bounding from below the rejection probability. And the question is, so the statement here says that the rejection probability for delta far words is pretty much delta. So you lose almost, if the function is half far, your rejection probability will be half. If it's 99% far, then your rejection probability with these log n queries will be 99% and so on. But this happens, there's a caveat, only for delta smaller than some absolute delta 0 that, as you'll see, depends on the rate. So let's see what we know about this. And this is where most of the focus of my research with my colleagues has been going into. So the initial paper showed only for something that is below the, what's called the unique decoding distance of the code. So you can see that even if rho goes to 0, the very first bound stops at 1/4. So anything above 1/4, you have no guarantees. Later on, we improved it with joint work with Swasti Koparty and Shubhangi Saraf 2 years ago. We improved it to something that goes beyond the unique decoding radius to 1 minus the 4th root of rho. And what's important about this parameter, I'll soon show you some plots, but that as rho goes to 0, this delta 0 goes to 1, which is a good thing. That's what we want to be. That's the situation we want. We want that as the distance goes to 1, your rejection probability goes to 1. So this is the first time it was achieved. But it went to 1 at a very slow, rate. And then we improved it recently to cubed root. And we showed that in certain settings, this cube root is even tight. over binary fields. There's and very specific rate parameters. This, you can't improve on this. We also gave in that paper a slightly more elaborate protocol that's called deep FRI, and there we reach the Johnson bound. We mean we have delta 0 reaching 1 minus just the standard root of rho. And we even under a conjecture, list decoding conjecture, we show what is an optimal result. You can't go beyond it, which is that for any delta. So like if you go back to the theorem, you can sort of, the conjecture is under the list decoding conjecture, what you can do is you can just strike off the very end of the sentence about soundness. It would just say, for all delta, rejection probability of delta forwards is delta minus little o of 1. So this is something we conjecture, and it's a terrific open problem. And now I want to explain how FRI, the protocol, is related to the question that we started with, and which is the focus of all the works, including the one that I sent to Veronica to share with you yesterday. But let me pause here and just ask, are there questions so far?
Yeah, I have a quick question. So for the existing Stark proposals, or like Aurora or ZK Stark or the others, so do they use the conjectured results or the theoretically proven results to set their parameters?
Okay, so basically the way you use the results is you apply. I mean, there are two things in the results that I'm not mentioning here. One is what is the field size that you need, and the second is what is the number of tests for target security. What is the number of repetitions of this query protocol, right? If you see the theorem, it talks about query complexity log n. So that's for one, one shot of, or one iteration of this query protocol. It costs you log n, and then you get sort of soundness of delta, or soundness error of 1 minus delta. And then if you want to get your soundness error down, you need to repeat it t times. So the question is, what is the parameter t? In all the works that I'm involved in Starkware and other places, and I think other projects that are using FRI and developing Starks and other protocols, folks use the conjecture, okay? But based on the work that we published this week, and which I sent with Veronica, for FRI, even if you do not want to rely on the conjecture and you want to go to the proven stuff, what you would need to do is, in the worst case, go to a degree 1 extension field and sort of double the length of your field of representation of a field element, and double the number of repetitions of your query protocol, and that's all. So there's at most a factor 2 in the size of the field. I mean, sorry, quadratic in the size of the field, which refers to factor 2 in the bit representation of the field, and a factor 2 in the number of repetitions. Yeah.
So does that mean overall communication in the real proof that, let's say, like we use in real life, not the proof length for the IOP part, but the proof length for the actual protocol? Does that mean that that proof length is multiplied by 4, or?
Typically not, because not by factor 4 for 2 reasons. First of all, if you look at the proof, it's more like, I would say, more like factor 2, but maybe factor 2 plus epsilon, and I'll explain. So definitely you need to double the number of repetitions. Actually, it's not even quite factor 2, because so you need to repeat the number of queries by factor 2, right? So you would think that this doubles, and also the field elements at the very end of, most of the proof is Merkle authentication paths. So you need 2 times many leaves. There are 2 things to acknowledge. First of all, when you double the number of leaves, you're not doubling the number of authentication paths. Sorry, the amount of communication, it's slightly less than factor 2. Why? Because you need only to share the sort of subtree that leads to all these leaves. And when you double the number of leaves, you're not doubling the size of the information in this thing. It's slightly less. Now, also in the leaf, you at most, in many settings, you're already using a larger field, or so you don't need to enlarge it by much. But even if you need to enlarge it by factor 2, it is only at the very leaf. And for instance, I'll give an example. In many settings, let's say we're using, we're right now putting 128 bits in the field. So now it needs to be 256 bits. But each authentication path is something like 20, 20 length 20, because maybe you started with a file of size 1 million entries, and it is 20 times 256 anyways. So the effect of increasing the leaf by factor 2 is less noticeable. So to summarize, the overall argument length, if you do these two things, would roughly grow probably by factor something between 2 and 2.5.
Okay.
But it's a guesstimate, or let's say between 1.5 and 2.5. I would guess that it's in many settings slightly above factor 2, like 2 point whatever.
Okay, nice, thank you.
Yeah, but I also want to say that it's a very simple change. So like, increasing the number of rounds, it's basically just a very simple parameter. And then, because the verifier in all these settings has already, it's expecting a certain parameter T number of iterations, and and all of these iterations are the same. So now you say, okay, I need 2T of these things. Okay.
So I have another question, sorry.
Yes.
So these improvements in the bound on delta zero, have they got anything to do with the decoding capability or different decoding algorithms you use? Or what's the intuition from going from, let's say, in 2017 to 2018 to 2020?
That's a terrific question. And I just want to point out that this does not include the very latest paper, which is also right now in 2020, but and that's the one that was published just this week, which I'll mention a little. I can tell you what it says. It basically gives you the same parameters as you see for deep FRI, but for FRI. And then I just to clarify something, you might notice that there's a contradiction, because we say, if you read the very last bullet, it says delta zero is 1 minus cube root of all, and we say it is tight for FRI. And now I want to say, but this very latest paper says that FRI gives delta zero 1 minus standard root. So how does it jive? The answer is, the tight for FRI refers to the case that the field is all of the evaluation domain. If you go to quadratic size fields, what we prove in the new paper is that FRI goes up to 1 minus square root of 1. Okay, so now let me answer your question. The very first work was not algorithmic. It was sort of things that below the unique decoding radius are relatively simple and straightforward, and then you're welcome to look at the original FRI paper and see for yourself. It was relatively sort of straightforward, using no decoding algorithm and no fancy combinatorics. I mean, it did refer on this Bezout's theorem as a black box, in a variant from Polishuk and Spielman. Yeah, so it did use that, but it's sort of as a black box. The next two results are very combinatorial in nature. They do not rely on any algorithmic results. They sort of use the Jensen inequality and things like that. And the very last paper, the one that Veronica shared with you, I guess yesterday, uses algorithmic decoding algorithms, in particular Berlekamp-Welch and Goswami-Sudan, but sort of follows the algorithm, it instantiates it with the case that we care about. It moves to a higher field extension and runs the algorithm there. And then, so we use the algorithmic result in order to deduce a non-algorithmic or a combinatorial result. So there's a little bit of both, right? I mean, there's a little bit of combinatorial results and a little bit of algorithmic ones.
Okay, thank you.
Okay, so I want to explain from a high level how FRI works. And if you're familiar with FFT, it's really a folded FFT. So just like in FFT, we have the problem. What is the problem? We're given a function G, I believe. No, we're given a function F. I want to be consistent with myself, I guess. Let me call it F. You're given a function F that is evaluated on a domain of size N. And we would like to maintain this gap, right? That either if F was low degree, then the new, and we want to reduce to a problem that is of the same nature, but is smaller by factor. The evaluation domain is smaller by factor 2, and the degree is smaller by factor 2. So it maintains the rate as an invariant. It maintains the property that the evaluation domain is a multiplicative subgroup as a property. What changes is just that the size becomes smaller. And another thing you want to maintain, and this is the trickiest part, is you want to maintain the gap, which means that in all cases, F was low degree, the new problem will be just as low degree, meaning of the same rate or half the degree. And if F was delta far from low degree, then in 99.99% of cases, the new function will be delta, maybe minus something negligible far from the new code. And it looks like an FFT, right? So you can write, you can think of F, right? The verifier is saying to herself, well, if the prover really honestly was evaluating a polynomial, then the prover can also split this polynomial, FFT style into something that looks like, right, g of x squared plus x times h of x squared. And this is just like an FFT. And then we have this locality, because if you query f of x and f of minus x, you can actually compute g of x squared and h of x squared. And the way to see it is that you can think of it as the other way around, right? Because x squared equals minus x squared, if you know g of x squared and h of x squared, and you use plus x or minus x, you can get from that, right? F of x is g of x squared plus x times h of x squared. And f of minus x is g of x squared minus x times h of x squared, right? This is just like in the FFT. So you can use g of x squared and h of x squared to deduce both f of x and f of minus x, and it's an invertible linear transformation having fixed x. So you can also go from f of x and f of minus x to this thing. So two queries into the table that f gives you will give you one query each from G and H. And we take D to be a multiplicative group of size 2 to the k, which means that if x belongs to D, then minus x also belongs to D. Now G and H, because the domain big D is closed under negation, it means if you look at the set of squares, it is a multiplicative group of half the size, and that's D prime. So this is the FRI protocol. The prover has sent the first USB, which is an evaluation of the function f and the domain D. What the verifier does is sample a random alpha in the field and say, please, in your next USB stick, send to me the evaluation of G plus alpha H, so it's a random alpha linear combination of G and H, but evaluated only over the domain D prime. So the next USB stick can be half the size. And then we repeat this, the verifier will sample again, some beta, and another USB stick will come around. Now, the nice thing is that after all these USB sticks have been collected, what the verifier can do, and that's the query phase, is pick some random x naught, read from the first USB stick the entry at x naught and minus x naught, take the alpha, the relevant linear combination of them, and then check whether it equals the second function at the point x naught. Sorry, x naught squared, which appears. Does this make sense? Hello?
Yeah, to me it does. I don't know about the others.
Yes, yes.
So another way to think of it, right, in the FFT, you start with F, and then you basically go when you want to move from, let's say, the evaluation to the interpolation or vice versa. So you start from F, you go to two subproblems, and you solve each one of them on the subdomain D prime. What you do in FRI is you mentally say, okay, the prover could be doing this. Now I throw at the prover this random alpha, and ask her to take a random alpha combination of these two functions. And I can later check by making two queries into F and one query into this new object, whether this, on average or for typical cases was the same thing, was done correctly. And then, of course, this kind of testing is repeated across all log n layers. And that's basically how you get query complexity log n. Notice that the running time of the prover is a geometric sum. So at each step you have, at the first step you have n operations. The second step you have n over 2 operations plus n over 4, blah, blah, blah. Turns out to be n operations, or 6n, because, counting all the squarings and multiplications, that's what you get. And the query complexity is log n. Now, it's not hard to see by induction that you have perfect completeness, meaning that if f was a rate rho polynomial, then for any alpha that you pick, the new combination will maintain the exact same rho. So the degree to size of D prime ratio stays rho. So, and you do this by induction, you terminate basically when you have a degree, a constant polynomial or some constant degree polynomial. You read all of it, you see that the table agrees, and then you're done. The tricky part, so the only non-trivial part, so the efficiency, the query complexity, the verification process, and even completeness are relatively straightforward. And this is typical of IOPs and PCPs and interactive protocols and many of these other creatures, MIP protocols. Completeness and query complexity, everything but for soundness is easy. Not easy, but doable. Soundness is the tricky part. But now you see that to analyze soundness, it's exactly the question that we started with, right? Because here we had G and, a random combination in G and H, and we would like to say that if one of them was far, then all of these linear combinations will be far, right? And that's the question we go down to. So now I just want to, plot these results. So what we have here is the x-axis here is delta star. It is the worst case distance. And then the y-axis is what is the average case distance. And we would like it to be as high as possible. So this would be optimal, the green line. If whenever, for any value of delta star, your delta average is the same. And notice that the covering radius of the Reed-Solomon code is 1 minus rho, meaning there's no function that is farther than 1 minus rho. So your graph must end at 1 minus rho. There's no distance above that. So in original, the first work that looked at this kind of question in a different setting was by Reingold, Rothblum, Vadhan, and Wigderson in 2013. And they basically proved that with very high probability, your average distance is at least half. So, but you lose a factor 2 in this proximity parameter. And then this work that presented the FRI protocol we showed that at least for some range, your rejection probability is as large as your proximity parameter, as your distance from the code. But then it sort of stops. And these are the numbers for actually for the rate 0.2. And another interesting thing is to sort of imagine what happens to your delta max, the maximal value of delta. You see there's this inflection point or whatever it's called where the mark line goes, where delta max sort of where the curve flattens, the red line flattens. And what we would like to do is make this delta max go up and up as much as we can. And it's especially useful to think of the case that rho goes to 0, meaning that also the maximal distance can go up to 1. So as the rate goes to 0, you would like your delta max to go and become higher. And the original paper had a relation between delta max and rho that looked like the red line on the left-hand side. And we would like to push it as far to the to the right upper corner. The next paper gave us an improvement. You want to get to the green lines as much as you want, and then it got improved a little bit better, and then it got even improved a little bit better. And as I said, now we have the blue line also for FRI, not just for deep FRI, for anything that goes, any field that is at least quadratic in the evaluation domain. And we conjecture for both protocols, FRI and deep FRI, that the actual answer matches the green line. But that's conjecture. So now I just want to, I'll go over it again. Like, why do we care? Why do we care whether it stops at 1 minus cube root, square root, or 1 minus rho? And the effect is that if you go from cube root to no root, and then you get shrinkage by factor 3. I think that we discussed this at some length. The difference between the conjecture and what we can provably do is exactly sort of the exponent in the root there. So if you can get the exponent to be 1, which means that no root, then it means that you have proven the conjecture and you work with the best soundness parameters that we know for this protocol. So the rest of the talk talks about the variant to the FRI protocol called DEEP, which is domain extension by eliminating pretenders. Okay, I'll go over it very briefly. So there's another, so I described the FRI protocol, but there's a twist on it that gives us a little bit more. So I'll just, you know what, but before that, let me just pause to ask if there are questions. Hello, any questions?
Questions?
Okay, can you hear me?
Yes. Yeah.
Okay, so I'll assume there are no questions. So Veronica, question, should I just stop here or should I go a little bit more and say something about deep FRI? Or is there something else that you would like to
Maybe
use?
deep FRI would be good. Yeah.
Okay. So there's a concept called list decoding. And we say that a code, an error correcting code, is delta comma L. So delta is a parameter between 0 and 1, and L is an integer. Delta L list decodable if every Hamming ball of relative radius delta contains at most L code words. And think of L as being something that is small, like polynomial in the block length, polynomial in the size of D. And what the Johnson bound says is that, I'll say it for the Reed-Solomon codes, but it is true also more generally for any code. It says that as long as your relative radius is smaller than 1 minus square root of the rate, that's in the case of the Reed-Solomon code, your L, your list size, is small. It's smaller than the evaluation domain size. I mean, it could be exponential, right? It could be like all of the space or something like that, but it's very small. So that's the Johnson bound. And there's also the unique decoding bound, which is the radius up to which every ball contains at most 1 point, and that's half of the distance. Yeah, so this is the Johnson bound. This is what it says, that if your radius is epsilon smaller than the Johnson bound, than 1 minus square root of rho, then your list size is actually constant. It's at most 2 times epsilon, 1 over 2 epsilon square root rho, which is a constant for constant 1, constant epsilon. And the conjecture we make is that, and it doesn't contradict anything we know, that actually you can list decode, the list size is small up to capacity up to 1 minus 1. That's the conjecture we use in basing deep FRI on having lower query complexity. So here's the problem we solve with the deep method, and the deep is domain extending for eliminating pretenders. Well, what if, what I try to do is actually pick G and H such that there are many possible polynomials that relate to them, or this f of alpha has many, it's like the centroid of a ball that has many Reed-Solomon code words that are in that ball. So maybe the way I'm going to try and cheat and break soundness is by not committing to which of these polynomials I want to go with, because maybe I'll do that later on. So here's a picture of these pretenders. So the method that we use in order to break this and eliminate pretenders is to, once we have F in our hands, we're going to sample all over the field and basically ask, well, what is F alpha of Z at a random Z? So, and this Z is not in the evaluation domain. It could be anywhere in the field. It could even come from some extension field. And the point is that it's very easy to show, just using a union bound, that with very high probability, given that the field size is large enough, the answer to this question will disambiguate, meaning there will be only one pretender that has good agreement with F alpha and also has the value that the prover answers. So now the challenge is just that, all we got is USB sticks evaluating F and then this next F and so on over very specific domains. But now we ask, what is the value of this function somewhere completely outside? So whatever the answer is, how do we incorporate that into the commitments we have already received? And that's the trick that Deep does. So what we do, this is the problem here, right? Z is outside the domain. So what we do is we correct based on the answer. And it's a very simple correction from an algebraic point of view, right? We define a new function that is one locally related to the previous function, meaning if I need to know the value of the function at the point, I can just query the old function that I have on the USB stick and have a correction. So here's the correction. What I do is I shift the function to have it 0 at Z, to have X be replaced by the variable X minus Z, and acknowledge the fact that at the point Z, the value was V, little v, which is what the verifier answered. So the correction is just F of F alpha X minus little v, which is the answer that the prover gave. divided by little x minus z. So this is a local correction. The only thing I need in order to compute f tilde alpha at the point x is I just need to query f alpha at the point x. And I already have f alpha at the point x on a USB stick. And it's not hard to see that f alpha of x is of low degree if and only if f of x is of low degree, and additionally f alpha of z equals v. So by asking what is the value at z and getting the answer v, we will, with very high probability, disambiguate the list and force the prover, if she was choosing, you know, a centroid of a list of polynomials, we will force her to go with one of them. And that's the deep trick. So you can, you know, change the algorithm to be this way. This is just the proof that it's a one local transformation. So the conclusion of all of this is that, for the deep at least, that requesting the value of f of x on a random point reduces the number of candidates. That's the elimination or disambiguation procedure. And then checking the value of f of x is possible even when p did not commit to it. You just do this local correction. And then the reason we get to do this, this is something you can't do easily in the PCP model or in other standard models, is because the IOP of proximity model allows you to have this interaction and have P adaptively respond to the queries of V, such as this query of, you know, what is the value of F, some weird point that's outside the evaluation domain. And you can also use it in other protocols in the Stark world and other places, and it's a very useful and simple technique. So with this, I end this talk and my series, and I'll be happy to answer questions. I'll also send Veronica a bunch of links, one to the Crowdcast talks on arithmetization, also on FRI, and I'll send you know, this slide deck and also the pointers to the various FRI-related papers. So those who want.
Yeah, thank you. That was great. Any questions?
Yeah, thank you, Eli. So can I ask, so now that you mentioned this brand new result on the original FRI with the improved bound, so what is the remaining advantage of deep FRI versus FRI?
Yeah, let me, so there is just, can you see what I'm sharing?
Yes, the paper.
So when I go to, can you see the paper, right?
Yes.
Mm-hmm.
So just below this conjecture, we say that, okay, if you look at the provable domain, currently FRI and deep FRI have soundness up to the same bound. There's even a number of minor advantages to FRI over deep FRI. It's slightly more efficient for prover and verifier because you don't need to do this sort of correction. The field size, if you look at the details, needs only to be quadratic, whereas for deep FRI, the provable results require cubic size fields and more. And in deep FRI, there's even a tiny loss in soundness with each step of the protocol, whereas you know, that's what we prove. Whereas in FRI, you don't lose anything. So it seems that FRI currently is strictly better in all aspects than deep FRI. I find it hard to, you know, that's our current state of understanding. I find this hard to believe for the simple reason that deep FRI does everything that FRI does, but asks the prover to do more. And this more part means that at the very least, you should, you know, your soundness parameters shouldn't deteriorate. So I think we just haven't, you know, looked at it again and proved it and so on and so forth. So I think that one should prove strictly better results for deep FRI. But we haven't looked at it yet. It's a really good, you know, research problem. Another aspect in which deep FRI is actually better than FRI is in the conjecture domain, right? Because even though we conjecture both for FRI and for deep FRI that they go all the way up to capacity, even for very small size fields, in this department, deep FRI has the advantage that we know of a different, well-known conjecture that a lot of theoreticians have looked at. And if that conjecture holds, then the deep FRI soundness goes all the way up to capacity. And also vice versa. If you show that deep FRI soundness is not as good below capacity, you must necessarily also find new, interesting, unknown results on the limits of list decoding. And like you will need to find a centroid of a relatively small Hamming ball in which you have super polynomially many code words.
Right.
So just to sum it up, it seems right now in our provable understanding, FRI seems to have an edge over deep FRI. I don't believe that can be the case. It must be that anything FRI gets in terms of soundness, deep FRI must get and better. Okay, even just looking at the papers, but we haven't done that. And the second is that deep FRI, the conjectured world, relies on a slightly more, more studied and looked at conjecture.
Right, I see. Okay, thank you.
More questions?
I have a question if we have time.
Yeah, maybe I shall come.
So when you want to repeat, for example, the FRI or deep FRI protocol, does that mean that the verifier basically chooses, like instead of choosing one alpha, he chooses like alpha 0, alpha 1, and like alpha t or t minus 1 or whatever? Are they the same things or?
One has to do that with care. So there are two kinds of, one is repeating the query, just a query phase without invoking the sort of FRI commit phase, without asking for any more USB sticks. And that works very well and as understood. There's also another, one might consider also repeating the, what's called the commit phase. So from your very first USB stick, generating, with alpha 1 USB stick and following through that. And then, or in parallel or in some combination, also asking for another, alpha prime combination, doing it separately. So there one has to be very careful in terms of soundness. In the interactive setting, this works perfectly fine. And soundness will sort of, do what you believe it does under repeated. So soundness error will roughly go down quadratically, or the number of different commits. Where it gets really tricky is if you go to the non-interactive setting, if you want to use the Fiat-Shamir heuristic or the random oracle model and claim better soundness. Then this particular thing will break. There are other ways of doing it. And actually, we're currently writing a paper explaining exactly this particular thing of how to, it addresses several other things, but this also. So it's slightly more tricky to get it done in this case.
Mm-hmm. But is this non-interactive case, is it specific to FRI or is it specific to if you want to use Fiat-Shamir in any protocol?
It's well, it's not just for FRI. Many protocols, when you go to Fiat-Shamir, just doing sequential or parallel repetition can completely break. There are a lot of cases of protocols where if you use Fiat-Shamir, it will completely break. Whereas as long as you stay in an interactive setting, they work fine. So it's not particular just to FRI. But in most cases, I'm aware of it's relatively, it requires care, but it's possible to fix that problem. And indeed, that's something we're currently addressing in this work that will hopefully publish soon.
All right, thank you.
Okay, yeah, time is up. Thank you very much. That was very informative and very interesting to us. And
Thank you.
yeah, you
I
answered
enjoyed
my
it
questions.
tremendously. Yeah.
Yeah, thank you.
Okay.
Yep, thank you very much.
Thank you very much.
Okay.
Bye bye.
Bye bye.
Bye.